Okay, ladies and gentlemen, appreciate this is part 2 of spray dryers, spray drying, I should say. Basically, some comments on control systems. I don't want to get into the area of control systems, but one of the problems with dryers, generally speaking, is getting the proper process measurements, like outlet moisture from the air or the gas stream. Anyway, so we use the outlet temperature, not moisture, but temperature. Outlet temperature controls the feed rate, or the feed rate of material to be spray dried, and the inlet temperature to the dryer controls the fuel consumption rate or combustion rate. So one way of two basic control systems, two different types. Or potentially use the outlet temperature to control the feed rate to the heater. The outlet temperature controls fuel rate to the heater. The feed pump is either fixed or manually controlled. So if we look at those two control systems, we have the spray chamber, the exit exhaust air from the chamber, the spray drying chamber, goes to a temperature indicator control, which then goes to the feed pump for the fluid feed pump. If the temperature is high, then you feed more feed, and it will cause the exit temperature to drop. At the same time, you have the heater, and basically you hope to fix the inlet temperature to the dryer, right, or the drying chamber. You go to a temperature indicator and controller that then goes to control the control valve for the fuel. So these are two basic control systems. The cold temperature says to add more fuel. Hot temperature says to reduce the fuel, anyway. As opposed to that, you use second control scheme is you use the exit air through a temperature indicator and controller going to fuel supply. Then it goes to changing the inlet temperature of the dryer. So here the dryer inlet temperature is pretty much fixed. Here the inlet temperature of the dryer is variable, or more variable, I should say, depending upon exactly what's happening with the fuel pump or this feed flow rate. This is indicated manual control. So you fix the feed at fixed rate. That should fix the exhaust temperature, which then fixes the feed flow rate to the heater, and it also would fix the inlet dryer temperature. But it strikes me, I don't know which control system would be better. The TI and the TO, the temperature inlet to the dryer and exit of the dryer, are the two design variables to a spray dryer. Talk a little bit, some additions to your control system. You might put in a wheel balancer for rotary atomizers. You might put in a broken bag detector for your bag houses. You could, for nozzles, you calculate the flow number for your nozzles. Flow number is really flow area for your nozzles. You can calculate that. You can possibly calculate that online. It's to monitor the wear or clogging of your nozzles. The area of the nozzle is fundamental to determining the drop size. Or you may add a gas to liquid ratio monitor, or air to liquid ratio for two fluid nozzles. That should have a minimum of L2, air having twice the mass flow rate as the liquid. Typically with two fluid nozzles, you're looking for the gas stream to cause the atomization. There's very little pressure drop available to cause liquid to cause the atomization. If the gas fails or the air fails you in a two-fluid nozzle, it will drip. It will likely drip. Advanced control systems, well, there's all kinds of layers of control you can put in. You can have feedback, feed forward, cascade control, control sequences, timing sequences, interlocks, alarms, etc. Electrical checks, all kinds of sub-control systems, controlling the feed, which we've seen, controlling the gas fans, atomization control, controlling the pressure drop. That may require a pressure controller. Weighing systems, pneumatic transport system, powder discharge system, bag houses, scrubber bag houses control, and cleaning systems of rotary airlocks. Then you might get into man-machine interface situations or controller sequences and decoupling. So, all kinds of feed forward and stuff, feedback, computer control, feed forward, multiple input, multiple output, data, big data. I'm sure it's evolving. You start with what the vendor supplies of the control system and then add, as I said, these are several of the items you might wish to add. To what degree, to what level, and to what degree new advanced control systems have been used in spray dryers is really company specific. Some companies don't want to change anything. Some companies are interested in control. Interlocks. One of the interesting things is concept of interlocks. In elementary chemical engineering control courses, interlocks are hardly ever mentioned. But they ensure a level of safety. Let's see what some of them are. One interlock ensures the exhaust fan cannot be turned on before a supply fan. If the exhaust fan is turned on, this will create a negative pressure in the chamber. And of course, it might be overridden if the door is open, chamber door is open. Interlocks prevent burner ignition unless the burner fuel pump is on, whether there's the combustion fans on and where the dryer fans are on. You don't want a situation where there's heat generation going on, but it stays there. Heat accumulating could lead to problems. So you want to obviously burn the stuff, but and then get it out of there. Interlock to prevent feed from a rotary atomizer, to prevent feed when the rotary atomizer is not running. So what would happen is the atomizer is not running, the feed would just drip off the wheel down into the chamber and lead to problems later. Interlocks to prevent the main dryer fans from being on when the cooling fans are not. Cooling fans cool potentially hot areas to prevent buildup of burnt material. Interlocks to prevent personnel from entering the dryer chamber when the dryer is in operation. If you enter a dryer in operation, it might be like entering a snowfall or having snow falling. Interlock to shut down dryer when a failure of water flow to the wet scrubber occurs, obviously. Or switch to water feed. Ooh, I don't know if I would want a water feed unless I'm cleaning. I guess if I take a look at a rotary wheel, right, you generate cleaning sprays. So it'd be interesting to see. I'm always interested in whether I can clean my equipment or not. So thinking about using your atomizer instead of generating particles or drops to generate flow rate to the wall or wash down your inner spray dryer. More interlocks, more control systems overlapping upon each other. Anyway, additional comments on dryers, psychrometric charts, and some data. Just rattle off some few things here. Spray dryers are used, one, for their high inlet temperatures. Two, many materials require required size, shape, density, and other properties that cannot be made any other way. So, like we said, the agglomeration process in a fluidized bed, or excuse me, you do spray drying followed by a fluid bed. Spray dryers are limited to liquid feeds and high evaporation loads, energy and flow requirements. Are limited to liquid feeds, have high evaporation loads, energy requirements. Spray dryers are used for a wide range of materials and many designs are available. Liquid should be sprayed in a uniform pattern, hopefully. No maldistribution of feed, and a uniform non-pulsing flow of heated air. Now, having said that, maybe pulsing air might be helpful in some cases, but for the most part, you want a nice uniform flow of air. Not all liquids can be spray dried, all right? Sticky or tacky materials, basically when you dry them, they become sticky and tacky, and that would lead to all sorts of problems. Some materials go through a sticky phase during the airborne stage and can only be spray dried. Interesting. If we go to Lefebvre's book and look at different fluid properties like viscosity, surface tension, air to liquid ratios, right? We find that we have the Weber number. The Weber number is right here in the parentheses. The OSOG number, which is sitting here. The Weber number takes into account solder mean diameter. Excuse me. Over here is the solder mean diameter. Here sits surface tension. And OSOG number takes into account viscosity. And the ALR takes into account air to liquid ratios or gas to liquid. Properties can be modified somewhat. I mean, surface tension is pretty well fixed. Can't vary that too much. Viscosity you can change due to temperature. You can run hot versus running cooler. Properties may be modified somewhat, either heating or cooling. Diluting usually is not desirable, right? Typical particle size for spray drying is 20 to 150 microns. Larger size particles come from larger drops, which need larger diameters or tall chambers. Large drops come from large orifices. Small drops come from small orifices. Big drops come from wheels rotating at low speeds with high flow rates. So it all sort of fits together. Small sizes cannot be made at high capacities, except at high atomization power inputs. Nozzles are more economic and spray in different directions. Maintenance is much simpler if there's no high pressure pump. Feeds are non-uniform. Nozzles tend to plug and do not operate uniformly if solids content and viscosity vary. You can have them start spitting at you, so to speak. If you have air in the line, that's also interesting. As you pull down on a tank and the tank empties the feed, and there's good possibility of air entering the line, and things aren't so great under that set of circumstances. Abrasion enlarges orifice. As I said, I was talking to a young lady in France. She was from France, and I was talking to her. She had a valve in her line. She had a 300 PSI pressure drop across the valve, and she wanted to know why the valve disappeared after a month. Basically, such high pressure drops had high velocities and high abrasion levels. Multiple nozzles are often needed for high production rates. Frequent cleaning replacements are normal. Right? You can't expect a nozzle to last forever. There is a tendency to believe that nozzles do last forever, but they really don't. They disappear. They become part of your product. Two fluid nozzles get their energy from compressed air, or let's hope so. Right. So too expensive at high capacities. That's what two fluid nozzles are. Two fluid nozzles accommodate feed rate. I don't, maybe this is too expensive is sort of a vague term, right? Two fluid nozzles accommodate feed rate and changes better than regular nozzles, right? Gives a broader range of particle sizes. Wheels and discs can be used in virtually all applications. Some types produce very uniform drops. Ligaments like cotton candy. You should review my course on atomization, and you should also review my course on drying 1 and drying 2. Wheels are preferred at high capacity because the horizontal spray speeds are very high. 20,000 RPM, that's fast. Drive mechanisms are far more complex and costly compared to nozzles. Sometimes need a high-speed motor run at high frequencies, require accurate balancing and skilled maintenance. Wheel balancers are available, all right? So no shutdown is needed for balancing. However, there's a diminishing return on this. Yes, wheel balancer can balance your wheel, protect your bearings. However, after a while, the buildup could be so substantial that the next failure could be catastrophic. In other words, the wheel balancer will give you a sense of complacency and let problems grow, and they grow. And then voila, you have a major shutdown where the wheel balancer no longer can do the job. Wheels can only be used in chambers large enough to accept horizontal sprays. However, the horizontal sprays can bend the airflow. So you have a sort of an assignment for you. I want you to go put your lawn sprinkler outside, sprinkle your lawn, and get an idea of the distribution that's produced from your lawn sprinkler. Then I want you to go view the same sprinkling going on when you have a high velocity wind. And you can get the idea of how horizontal sprays can be bent with high flows or airflow. Chambers, who's got the chambers? Short chambers, tall chambers, rectangular boxes, all kinds of things. Widest range of applications, conical towers with coherent air patterns, right? Conical towers. Residence time, 5 to 30 seconds, maybe as high as 60 seconds for towers. Now, we're talking about residence time of the gas flow. We don't know for sure what the residence time of the particles is. So you might put in a tracer in the particles and see when they come out. Put in some red beads or something like that, or somehow put in some particle indicator. To make larger particles at low capacity, small diameter, tall chambers are used. Mixed flow chambers increases exposures. So, let's go back. So here we have our chambers, tall towers, and a G would be a box, some sort of thing like that. Chamber. Who's got the chamber? Here we have part of 4.2, figure 4.2 is here. And you have some comments. Conical, cylindrical, cyclone, tower, box. Where it's used, what sort of atomization, what type of flow you have. Give you an idea of the flow pattern. Spraying upward, it gives you the maximum travel distance. Co-current upward, again, without a costly large diameter chamber. Spray dryers with fluidized beds have been mentioned. Another spray dryer with belt dryer is possible. Chambers mounted directly over the mesh belt, mat to convey material through the various zones for processing. Anyway, what we have here, just some data, basically. The type of material you're spraying, skim milk, eggs, coffee, tea, right? Sort of moisture content going in, 75 microns, 75% moisture, 85% moisture, outlet percent moisture. That's a substantial moisture reduction. Inlet temperature, 270, 110 leaving, degrees C. Parallel flow, co-current, I guess that's what that means. Interesting to compare your performance with some of these. Anyway, some more data. We have the material. We have coffee again. Inlet temperature in, exit temperature out, percent water in the feed or percent moisture, evaporation rate. So this is 18 feet diameter, 18 feet high, spray wheel, fan capacity. So Wallace's book, 1988, excellent book, Wallace's book in 1988. I'm sure I lifted this from there. If I'm not mistaken, some other data. Dry products, micron size. Typically, you're looking, power input, you very seldom see that, but it's like kilowatt hours is energy, basically, per volume. Basic fundamental unit of power input. Bulk densities versus inlet air temperatures, you see some relationships versus percent solids in the feed. And again, I highly recommend you review my course on drying, right? And if you do that, you'll notice the two big things that matter is inlet temperature of the dryer and the outlet temperature of the dryer. And when the two cross, you have this combination of inlet temperature and exit temperature. You have that evaporation capability. I'm assuming water. And up here, I have 500 coming in and 200, and I have that evaporation rate. Okay, I'm not sure. I'll have to go back and check the reference exactly what BLSA is. I'm sure somebody will tell me if they get this far in my videos. Anyway, product number, I guess that's some sort of placement along this x-axis. Okay. Psychrometric charts, yes. Again, the following is really from my drying course, my general drying course. I won't need to go through these simple calculations that were done in my drying course. And basically at the end of all this, excuse me, let's try that one right there. Try one back. Try that one. Obviously, a couple things. You pick the inlet temperature. You pick the exit temperature. Those are 3 points here. So if, I'll show you this chart later, fairly quickly onward. But again, review my course on drying. This is from there. Summary, here's a summary. Design is roughed in. You, after you do go through my course, roughed in the amount of water evaporated or moisture evaporated, the airflow rate, and the heating rate. These are three the big things for a dryer. Now, you have a clothes dryer at home. And what does the clothes dryer do? Well, it's very similar to any dryer, direct dryer, right? You heat up the air. You have to have a flow rate to heat up the air. And then the hot air goes in to your dryer to evaporate moisture. So in the dryer design, typically you pick. Now, you got a young design students, the picking is your choice. Exit moisture, inlet dryer temperature, exit dryer temperature. You usually know inlet temperature and conditions, inlet moisture, and usually you know the bone dry mass flow rate. Anyway, the reason why you use such a chart as this is one of the major reasons. Here you have moisture per dry air. Here you have enthalpy per dry air. Now this is really moisture per time, per dry air per time. So moisture evaporated basically per time versus dry air flow rate per time. And on the x-axis, you have the heating per time divided by air flow rate by time. So you have the three basic variables. You have the airflow rate, that's bone dry air per time. You have the heating rate per time, and then you have the evaporation load. So suppose, for example, you want to quickly envision taking your supply air, which was at 60, and now you're going to bump it up to, going to keep it at the same moisture content, but you're going to bump it up using a heat exchanger where you move it from here to there. And you want to see what effect does that have, right? Well, if I project it up and I'm heating with natural gas, basically the propane or whatever, there's moisture increase due to the heating requirements. So this line is tilted upward. Now that moisture requirement this is no heat exchanger, you have this situation occurring. So I have these two situations. X is for the variables where I have used exhaust heat to heat the supply air. That's what that was done, the heating done like that. Now I'll give you an idea of whether that's economic or not, right? This is free. Well, you have it, so you might as well use it. So you line up the two streams and you boost your inlet from here to over here. Now, as a percent of total burn, you can quickly do an analysis. This length may be about 20 to 60 or 58. So that would be, what, 38? And then the total would be 20 to 170 or so. So you have 38 divided by 170. So, 170. Well, I got to take that 170 minus the 20 here. So minus 20 makes it down to 150. So I have 38 divided by 150 in this region. So I get an idea of how much energy I'm saving. And we can do a quick calculation on that. How much you save, I picked off X, X4. Entering at 1, you enter at X1. Excuse me, you're entering at 1, now you're entering at 1X. Save about 34 BTUs per pound of dry air. Then you come along and multiply by airflow rate. So you're saving Airflow rate might be 39,000 or 3,953. You're saving 34 BTUs per pound, or I'm saving something like 1.3 to times 10 to the fourth BTUs per hour. I don't know if that matters to you or not, right? How much cost that is. Remember, natural gas went down by a factor of 10, right? Up around the 20s, going to 2. So you have substantial natural gas costs reduced. Now, if you're not heating with gas, but you're doing electrical, right? Your electric bill went down by a third or a fourth? 36 divided by 30, 150. Anyway, here we go. Now the exit temperature you pick. So you have the inlet temperature coming in at 300 Fahrenheit. The exit temperature you pick. Okay, let's take a look at this. Straight up is just heat loss only, right? B is heat loss with heated feed. Now, heated feed will give you a slight tilt here. In other words, you heat the air, which is this line, and then you put in a little bit of heat with your feed. So now, instead of one source of energy, you have two sources of energy, one being the air and the other being heated feed. So that's going to slant the line sort of like this. And the heating rate of your feed has got to be the difference between 2 and 3B down here on the x-axis, if you wanted to do heated feed. If you wanted to do heat loss and heat exchanger, I put an internal heat exchanger inside the drying chamber, then the heat exchanger obviously is going to put in heat. So the amount of heat that it puts in puts it over here. So it'd be up here around 3. You can see I've certainly moved away from A and B situation here, and I'm already up in this region. So I'm going about 28% moisture, 0.28 moisture, say in this region, up to 0.043 moisture in this region. So I have a substantial increase in moisture being picked up. And again, this is an exchanger inside the drying chamber, right? B, I have heated feed, and here I'll have an exchanger inside to do some more heating. So, and by having an exchanger inside, even though I have exit temperature still at 200, I have picked up a moisture, say, from 2.8 to 4.3. So I've picked up substantial amounts of moisture here. Okay, now these are psychrometric charts, right? So if I have any interaction between, say, a hydrocarbon and another gas, I would have a psychrometric chart for that. Well, I'm not sure, long time since I taught food engineering, but I think at one time there was a process to remove caffeine from coffee, and they used hexane to remove caffeine from coffee. And then they dried the hexane and they had to remove the hexane from the coffee. So they would spray dry it. They would get coffee out the bottom and hexane out the top. So hexane was being removed from the coffee liquor. So we have the heating going on, then we have the drying operation. Now then, since it's hexane, we want to have a condenser, and the condenser will condense out the hexane back to the original starting conditions. So we pull hexane off as a liquid. Coffee will come on out. Instant coffee will come out as a solids flow, not showing here. But I'm just saying that these types of psychrometric charts are available for all kinds of different stuff. All kinds of different stuff. Okay. And all you got to do is create these. And you have these lines of temperature sitting here. This would be your inlet temperature, your exit temperature. Anyway, shortcut, two variables of importance, inlet temperature and exit temperature. Here I have an inlet temperature heavy line of 400 and my exit temperature of 200, so I'm sitting right there. I drop down, shortcut chart for air water again. I have the airflow rate versus the evaporation rate. And then over here, I have the heat load versus the evaporation rate. So I got to figure out what I want as the evaporation rate. That will then fix, this is 7.2. I can calculate the airflow rate, and I can calculate the heat load, or how much heat I got to put in for that. So this entrance, inlet, and exit, kind of cool. I think Cook had a lot of computer programs, and if I'm not mistaken, what's that language? Basic computer language. I don't know if they're still available, but anyway, part of AICHE. This is a close-up shortcut chart again. Charts provide understanding, easy visualization, and interpretation. Very useful and quick. No computer simulations. It's not opaque. It's very easy to see what a little bit of preheat to the feed will do, whether I have an internal heat exchanger or whether I have a condensing system, condensing the benzene and taking it out. So this is a cycle in here. Get out the benzene. Anyway. Effective operating variables on heat consumption, the effective inlet temperature, basically increase in the inlet air temperature decreases heating requirements. 10 to 20% leads to 10 to 20%, right? Reduction in fuel. Always feed at the maximum percent solids possible, right? Very important. Okay. Let's see, what else do we have here? Spray drying is expensive. Moisture reduction saves money. An increase from 50 to 60% can reduce heat load by 50%. That's pretty extraordinary. So maximum solids is where the feedstock can no longer be easily atomized or pumpable. Dewatering techniques might be of use. A concentrator might be of use. In filtration, one of the things you try to do is concentrate your solids. Increased solids in feed can lead to heavy chamber deposits, right? Increase in solids lead to increase in drop size, lower evaporation rates. You run into the particle becoming an object in the flow and it hits the wall. Often spray dryers operate at low solids and low temperatures because of feed properties. Depends upon the ability of delicate, dry delicate products to withstand degradation. Three primary ways of removing solids without heat: filtration, centrifugation, and decantation. Of course, we haven't mentioned that there are thickeners. There are preconditioners often used in evaporation. Are often used in filtration. There are some difficult processes in their own right. Filtration can be difficult, can be very unpredictable. Some can be very easy, like letting the liquid just sit there. Decantation is really inexpensively easy. Drainage is very easy. Solids, again, solids handling is an issue. There are various thickening methods as well. Heat required to evaporate water is the same as independent solids present. Heat required heat going to the solids is small compared to heat going to evaporation. If you can avoid or reduce water content, do so. And of course, my best recommendation is avoid drying at all possible. So feed as dry as possible and don't dry unless you need it. Okay. Higher delta T, higher inlet outlet, lower heat requirement. It's a thermodynamic thing. I'll have to figure out what that meant. Maybe it's use shortcut charts to make comparisons. There you go. So let's go back and see, using the shortcut charts, whether that makes any sense. Higher the delta T. So what does higher the delta T mean? If I'm going from, say, this point to this point to this point to this point, what happens, right? So the difference here is 50, the difference here is 75. So I have a higher delta T and I have a higher heat load. And then I go, so my line's going through here, I go from 50 to 75 to 100. So I'm following that line up. So it gives me a trend. I have higher delta T's going this way. So I always like to check things to make sure they are true. And let's see if that was true. It's supposed to give you a lower heat requirement. Let's see if that's true. Going back through here, I have heat load for evaporation rate. So I'm going from here to there with increasing delta T. And it looks like my heat load's increasing. So, and then look at that, it drops down. Here I have 150, here I have 200, and here I have 300. So I'm going from here to there, and I'm also increasing along that line. So I put question marks on this. When I was first teaching this, I didn't believe that. I didn't believe that statement. I had no way of making sure it was right or wrong. So I put questions marks, and right now it seems to be wrong. I use shortcut charts to make comparisons. Increasing delta T is increased by increasing inlet and lowering outlet. Lower outlet means higher residual moisture and product leaves. Increases further process requirements after drying. Maybe, maybe not. You may be able to use that moisture to advantage. You may wish to sell that moisture. So it become part of the sale weight. Some of my best friends love to sell Lake Michigan to the American public, right? And, you know, if you're making ice cream, air is cheap. So you put a whole bunch of air in your ice cream. Just as a comment, so maybe I want to sell water, right? Another comment, ice cream, you're allowed to put 50% of air in ice cream. If you take a look at that from an economic point of view, air doesn't cost anything. It makes the product more, you can scoop ice cream easier when it's aerated. 3, it doesn't add calories. The only bad thing you're putting air in ice cream is it reduces the weight, feel of weight, okay? So you have an assignment, I want you to watch ice cream melt, okay? It's a very simple assignment, and Watch the foaming coming out of inexpensive ice cream. Now, I don't know if Ben and Jerry's put foam in their ice cream. I don't think so. It's hard to dip. And as a result, less air. Besides, people like light and fluffy desserts. What do you think? Anyway, just as a social comment to break the monotony here. Effective partial recycling of exhaust air. Open cycle exhaust to the atmosphere is a large heat loss. Bam, a large heat loss. Outlet temperature may be high enough to achieve desirable moisture content. The recycling exhaust air preheats the air supply to recover some of the waste heat. Reduces fuel consumption. It's a good thing. Less heat loss to the environment that destroys the environment or helps the environment, but assume it destroys the environment. Fuel savings up to 20% have been obtained with partial recycle where the exit outlet temperature exceeds 120. 120 means there's a lot more heat in there. If it's 110, not so much. Right? Successful application requires above 120. Dried product is heat resistant. Okay. Fines and train and recycle can withstand inlet temperature. Well, it depends upon how you're doing the recovering the heat. Right. Remember, moisture is recycled too. Okay, that's great. Effective feed temperatures. Increasing the feed temperatures reduces the heat requirements. So you run hot. Basically, that's pretty simple. Run hot. Don't cool. Don't lose heat before the dryer. You might try installation there. Preheating helps, by the way, generally speaking, thermal insulation is put on for safety reasons, usually. And then you have energy savings. Preheating helps to reduce feed viscosity that results in better atomization, possibly prevents feed crystallization. Yeah, that's in the realm of likelihood. The line freezes on you. You heat it up a little bit. You trace the lines with heating. So it can help. You play what happens games. What happens if I lose feed due to line crystallization? Remember, I'm pushing the feed to higher and higher solids, and that way I'm pushing it towards higher and higher crystallization probability. Rarely is preheat done to improve thermal efficiency. Some heat exchangers can handle and train particulates. A shell and tube is not one of those. Well, let me rephrase that. If you put the particulates on the shell side, you're asking for problems. Anyway. These heat exchangers can recover waste heat. Investments can usually be justified. Payback times is site specific, but you're looking 1 to 3 years, right? Air to air and air liquid air. Beneficial when outlet temperatures are in the range of 90 to 130. Before we were saying it had to be 120 or above, right? Is that what we were saying up here? Where was it? 120. Now we're saying it's beneficial. Fuel savings to 20 to 30% is possible. So it tends probably to be site-specific. Guides for reducing heating costs. Have good housekeeping. Regular maintenance. You want good. Yes. Okay, we took a short break. We're back. Guidelines for reducing heating costs, good housekeeping with regular maintenance, inspection, especially burner assembly. Have good dryer cleanliness. Helps to prevent stoppages, avoids deposits. Have correct drying operations by maintaining correct temperatures and feed conditions. Monitor the feed and feed conditions. Question is your feed changing on you? And how do you know that it isn't changing on you? You don't want to over dry. Very important. You got a spec for the moisture content leaving the dryer. Don't give more than desired. Minimize long startups and shutdowns. Yes. Guidelines for correct process operations. Feed at the highest possible solids. Maintain insulation intact. Do not use higher outlet temperatures than necessary. Rectify all hot air leaks. Use as high an inlet temperature and low inlet outlet temperature as possible. Consider two-stage drying, partial recycle, especially if the outlet layer is 110. Now, we've already seen we had 120, now 130, now we have 110. Consider heat exchanger outlets is above 100. There you go. So now we have 130, 120, 110, and 100. So it really is a function of what your energy costs are. I mean, if you're out in the middle where they freely flare gas, then drying heat is free, I would imagine, or considerably low. Consider dehumidifying the air for humid locations. Use a scrubber to preheat, pre-concentrate the feed. Improve insulation. Filter air intake. That's true. Strain feed for materials that clog atomizers. Yeah, you might have a strainer in there. Outlet air is usually controlled by the inlet air temperature and feed rate. And fans, one at the inlet, one at the exit of the cyclone, 2 fans in a push-pull arrangement. Don't want fans to experience solids too much. Fans at the exit causes the drying chamber to be under a slight vacuum. By the way, dust will collect on rotating fan blades. If you have a box fan at home or a ceiling fan, you'll notice that solids in a home environment accumulates on the fan blades. Helps with leaks. To have the particle collection system collect the particles. Well, that's pretty cute. Have the fan free of solids as much as possible. Fans will collect on the fan blade. So what we're talking about, push-pull arrangement, you're pushing it in and you're pulling it out. Notice here it's after the cyclone, not before the cyclone, right? Because there's substantial solids leaving here. Only a 1-fan system, usually for small dryers on the exit, right? These devices, wheel balancers, fan balancers, these devices exist and keeps everything in good operation. Good idea to prevent too many shutdowns. All right. Catastrophic failure may occur if cleaning is neglected, right? Pump or constant head type tanks, usually two tanks, feeder, feed strainer. Design piping systems for easy cleaning and maintenance. May want recycled product to change the feed. That's interesting. Recycle back material to change the feed characteristics. Pumps are usually rotary positive displacement. Diaphragm pumps are for irregular shape and abrasive feeds. What bothers me is the word positive displacement and slurries. Now, that is an interesting combination. As positive displacement usually, implies close clearances, and close clearances means, with slurries, means abrasion likely. Numerous cases of pretreatment, blending with additives, correcting the pH value, all kinds of things. Atmospheric air is usually the supply source. Filter to remove airborne particles above 5 microns. Must mix air with atomizing fluid for rapid evaporation. Must dry feed sufficiently before our spray reaches the wall. Now, that's the time of flight calculation. How long does it take to evaporate and how long it takes to have it reach the wall. Arthur Lefebvre's book on atomization has an entire chapter on the calculation of time of flight. And it was with such calculations, there's a model, right, or several models on what happens when the material, as it evaporates, what happens as it goes to the wall. Theory must agree with fact. I suspect, just as a quick estimate, very crude, of course, the wheel tip speed will be the velocity of the particle leaving, and assuming no reduction, no drag reduction due to the surrounding air, that wheel speed will indicate how long it takes for the particle to reach the wall. That's if it's a big particle, okay, big drop. Just say the wheel speed is, that's the velocity of the particle, you got the distance between the wheel and the wall, and that gives you the time of flight. And you also have the idea of how many drops are made, and that would give you the evaporation, gives you, you have the number of drops or particles formed, or number of drops formed. Then you can calculate, or you measure or have an idea of the evaporation load involved. You can calculate the individual evaporation per drop. An interesting calculation, right? You know the evaporation load, you know the number of drops. So you know how much evaporation occurs per drop, and that's got to occur quickly. You don't want liquid reaching the wall. Must dry the feed sufficiently before the spray reaches the chamber wall, prevents wall buildup. Filters are washed regularly. You got the air filter, right? You got filter in the feed. Air chamber dispersers can affect drop size distribution, of course. Drops hitting other drops usually involves angular veins which swirl the air. Swirling keeps the stuff off the wall, of course. See, we're assuming that the rotational speed of the impeller is the same as the velocity of the drop. But we didn't say if the air is swirling, the distance to the wall is a lot larger, right? Because the drop will have a tendency to swirl as well. And it swirls over a larger distance than that between the atomizer and the wall. So the swirling air is going to help you out there. Okay. Anyway, I give you some comments on how to do calculations. Evaporation per drop. Rotary atomizers likely generate their own air flow rate. That's very true. Basically, rotary atomizers, to be cynical about it or take a different perspective, rotary atomizers are nothing but fans that push air around with a little bit of liquid on it. How's that? Anyway, drying chambers, all sorts. Main objective is to provide enough residence time for drying. Don't degrade the particle, don't have wall buildup. Particle discharge should be, product discharge must be continuous. Discharge method is conducive for product specs. Discharge is usually at the base of the chamber. General designs, co-current, countercurrent, mixed, all kinds of other chamber options are available. Many are patented. One main reason to talk to spray drying companies is for their chamber airflow knowledge. And chamber, who's got the chamber? There's all kinds of chambers. Anyway, just give you this list. Chamber, who's got the chamber? Product discharge, lots of different designs. Most discharge occurs at the base. Fines remain entrained in gas in the airstream. One design is sonic, liquid piles up below the air vortex. Another is the sweeper on the bottom with a screw conveyor. That's an interesting design. Another design may have side discharge or sweepers, centrally mounted discharge sweepers. Pneumatically conveying can be used. The product doesn't form sticky lumps. Air and product exhaust ducts must be high enough to convey the product. There you go. Cooler air and exhausts may help. cooler air, and exhaust ducts may help. Chamber wall aids in product discharge. Air wall cooling or air sweeps the wall can be used. Chambers and vibrators are mounted on the walls, cause vibration or hammering. Chamber wall must be low. For sticky products, double wall cooling, rotating air blooms, and tangential air sweeps help. Up here, you can also have chains. Inside, you could have dangling chains to help. Outside, you have hammers or vibrators, perhaps. See, the chains would sweep back and forth, hopefully. Used to maximize product and reduce excessive release of the powder to the atmosphere, right? So we're talking about recovery product from exhaust gas. Wet and dry equipment used, dry products bagged off and sent for further processing. The wet may be recycled as a feed pretreatment. Right. Anyway, wet may also be sent to further processing or considered an additional product or waste. We don't want to call anything a waste. It's just considered a, how can I say it, a byproduct. We have our typical cleansing, cyclones, bag houses, precipitators. Cyclones are real cheap, right? There's nothing to them. Just metal. Product quality is not affected except attrition effects. Cyclones can change particle size distribution. So we have wet scrubbers, wet cyclones, hydroclones, or fluid clones, irradiated air fans, sometimes installed as a secondary stage. You have a fan that's rotating, you spray water on it. There you go. Liquid concentration often too low for recycle or economic recovery and are passed to effluent treatment. I apologize for these, but what's really unique is basically you tilt your computer screen, right? You take this and turn it on its side, and then you got, instead of me fussing around seeing if I can rotate this, you can rotate your computer. It'll be the same effect. And what we look, bag filters, we can have vibrating bag houses, reverse air jet bag houses, we can have blowing air ring bag houses. Looks like we have all dots here, no dots here. And we're at the bottom, little bacterial growth, all dots there. Looks like all three are equivalent, except for right here, and this is for easy to clean. Star denotes suitability. And the, whatever it means. So high air throughput, high powder loadings, low powder loadings. Anyway, you can look at it on the side. Bag houses, now we have cyclones. Dun, dun, dun. Covers everything, look at that. Nothing wrong with a cheap old cyclone. Wraparound inlet, tangent inlet, they're probably the same thing. And then we have scrubbers and gravity settlers. And we have electrostatic precipitators, plate type. And we have our various requirements. See what cleaning is. Looks like we can clean except our electrostatic precipitator. I don't know if there's that's not a dot. So there you are, some tables to help you understand cleaning operations better. Cyclones and bag filters, widely used, low cost, easy maintenance. I don't know if bag filters are easy maintenance. Efficiencies are somewhat high enough so that secondary stage is usually not needed. However, cyclones are not 100% efficient. Bag houses or bag filters are virtually 100% efficient. We can get some numbers a little later. Bag advantages offset the cleaning difficulties and high maintenance. Bags can also tear, so you may need a bag detector. What is that one? Allburn Air or has a bag detector. It's just a metal device, and when a particle hits it, it changes the charge, and they record the charge. Allburn, AUBURN, has a broken bag detector. Very sensitive, very sensitive. So I hope you have one or have something equivalent. Bag tears come from loading, okay? Also, probably if you have your bags vibrating in there, their motion causes repeated causes a place where repeated motion will eventually tear the bag, perhaps. Downtimes for bag houses can be lengthy. Best bets use cyclones first, followed by bags. Cyclones handle the volume, bags handle the cleaning. Cyclones are far easier to deal with than bags. Battery of cyclones might be considered possible. Now, one of the interesting things you got to worry about the numbers here. When something says is 95% efficient, you go, oh, wow, that's great. However, you got 5.5% product still there, right? So it's getting through. So this may be great efficiency, but it still has some problems with it. Generally, there's no hard and fast rules for air exhaust cleaning. My favorite answer to every engineering question, it depends. If you take a look at engineering questions, they're usually underspecified. Okay, there's always further questions. And the answer to all engineering questions, it depends. And when you say it depends, it makes you look profoundly smart, right? Oh, this person knows something. He's going to give me options. So you run down through the options. Anyway, we have regular conventional cyclone, and those are the dimensions. Then we have this dual vortex separator. In other words, there's a vortex down here, and there's a vortex up here. And I'm not sure what exactly this line's supposed to represent, but I suspect the flow goes through it. And you have a large solids goes through here and here. I'm not quite sure what this does. Secondary airflow. To drive the vortex, this is probably some sort of rotator, give you a swirling action, and passing through veins to further give you swirling action. And what we have here, standard bag filter, we have micron size 1, 2, 3, and we have the efficiency. So if you get to 4 microns or 3 microns, you're already at 99% efficient. Then with efficiency grade curve for cyclones specified in example 12.7, we don't have. But there again, you 20 micron sizes, right? So I hate to ask this question. Do you have your efficiency curves for cyclones, number one? And number two, how much have they changed over time? Because this cyclone will eventually abrade away and disappear, perhaps. Or better yet, a more interesting comment is what you think is inside is not there anymore. Friend of mine, mixing consultant for a big, very famous company, and he was doing a site visit to plant, and he walked by this big, huge tank, and the shaft was rotating around, and the tank was filled with water or liquid. And my friend asked the plant manager, is there anything in that tank? Is there an impeller in that tank? And the plant manager says, oh, yeah, no problem. There's an impeller in that tank. So at noontime, they passed the same tank and had pretty much the same exchange. Yes. Of course, there's an impeller in that tank. So towards 4 o'clock the afternoon, when my friend was leaving, he was allowed to leave early. passed by that tank, and this time the plant manager got upset with him. And I'll show you there's an impeller in that tank. So he drained the tank. And as the liquid level was dropping, they looked inside, and it looked like a candy cane sucked down to a point during Christmas time, you know. So as the liquid level dropped, the diameter of the shaft became thinner and thinner and thinner. So the impeller was long gone, and obviously the plant manager didn't know what was in the tank, equipment in the tank. You would think that's fundamental knowledge, huh? Anyway, let's go on. Pilot studies, residence time, dryer outlies. Anyway, art, spray drying. Mass and energy balances are available. Heating rate of air drying rate, airflow rates, lots of information on equipment. Lots are still missing, so we still go with an art. Depends upon experience, basic principles, not based upon more theoretical approaches. Limitation, major limitation, the inability to express the interaction of drops with surrounding air. There you go. That may be changing. We'll get to some of the computer simulations later. An inability to determine the particle and airflow patterns in the drying chamber. Again, this is the idea. You set up a confetti flow system and videotape it, you can gain some understanding about what flow systems you have. Do a scale model, right? Hence, specifications and design of scale models are based upon existing industrial experience, testing, non-theoretical procedures. Designs are very dependent on manufacturers. The way you design something is fairly simple. You just let the manufacturers do it. I'm teaching a design course in college, and I never say that to the students. The best way to do design is let somebody else do it. Okay. I mean, when I went and get an automobile, do I go design the automobile? No. So the same thing. You go out and get somebody who knows a whole bunch. Missing parts, interaction of drop and surrounding air, particle and airflow rates in the chamber. These unknowns are solved by the manufacturer when you have the air dryer disperser, atomizer, and spray chamber are specified. These three items determine the interaction of drops surrounding air and particle flow patterns. There you go. So this is the icing on the cake, so to speak. Multi-phase flow, like evaporating drops in air in a spray chamber, is beyond commercial computer computation at the present time. This may no longer be true. However, a boiling drop, i.e. these drops are going to boil down to a solid, and that boiling is, again, doing the molasses analogy, might be quite different than what you think it is. Single procedure will never be universally applied. Any sets of correlations will have limited value. I like doing tests at the plant level. Objective is to have a practical approaches and guidelines. You're not looking for exact answers here. What you're looking for are trends. You tend to think this is better than that, that's better than this. So you eventually whittle it down to what's the best choice. And that's done by comparisons, right? Not necessarily by calculations, but by experimentation or plant operations. So the objectives have practical approaches and guidelines. Pilot plant tests figure optimum performance, importance of residence times. Basic type, co-current, counter-current, mixed, inlet and exit temperatures while obtaining powder qualities. These are the qualities: moisture, size, bulk density, color, flavor, texture, flowability. Required residence times for design properties while avoiding wall buildup, time of flight for particles from an atomizer. That's our friend Lefebvre's book, a whole chapter on calculation of time of flight. When you got finished with all sorts of calculations, you got to sit there and ask, is this reasonable? Is it plausible? The relationship between outlet temperature, residual moisture, yeah. Optimum feeding to have complete atomization with product quality. Continuous operation can be achieved. Ancillary hammers, air brooms, and sweeps. So, selection of atomizer, operating conditions, rotary, pressure, two fluid. I would do site visits. Get the vendor, give you a list of people using their equipment. Go out and visit them. All right, talk to the maintenance crew, talk to everybody. I prefer to talk to everybody. I learn everything from everybody. You know, it's just, I'm a constant absorbing information. So, you know, maintenance people are, you know, don't have a PhD from a university, but they may have an equivalent PhD in maintenance, right? Suitable dye collection, final exhaust air cleanings, samples for evaporation, market analysis. There you go, market analysis. There ain't no thing that you don't want to make unless you can sell it. You got to be able to sell it, right? Basis for operation product. All this information helps in scale up. Okay, let's see what we got here. So, override certain produces certain specialty products. So there we go. Different geometries. Slurries, slightly abrasive, pumpable pastes. So your wheel becomes a mudslinger in a sense, right? Pumpable paste. Care and scale up. Well, first off, you realize that the big difference in scale, right? More difficult to dry on small test dryers due to the closer proximity of the wall. Any deposits and tests must be evaluated as to whether they occur on a large scale. Yeah, this is very true. In scale up, lots of things happen in the lab that don't happen in the plant, right? Lots of things happen in the pilot plant that doesn't happen in the lab. Or excuse me, that doesn't happen in the plant. So there's a whole bunch of things that don't scale. Okay. I ran across the guy who was very proud of himself, and he should be. And of course, he was the person behind funding the process. Anyway, he was doing some studies, and it failed in the lab. I mean, it utterly failed in the lab. So he says, you know, should I scale this up intermediate level and see what happens? Might as well. So he scaled it up intermediate level. Again, pretty much a complete failure. And he's sitting there and saying, you know, the hell with it. He went full scale, and the process worked. So it failed on the small scale, failed on the pilot plant scale, and worked on the plant scale. Now, how do you figure that, huh? It means that scale up is a tricky area, and lots of phenomena that happen on the large scale do not happen on the small scale, and vice versa, small scale, large scale. For example, okay, this morning you may have gotten up and turned on the faucet in your kitchen or your bathroom, whatever. It's a 2-inch or an inch pipe, right? Flow rate comes out, no problem. You turn it on and off without paying much attention. You don't expect any water hammer or shock waves in your processing line. Okay, next door down the road from you is this huge gasoline pipeline or huge pipeline, whatever's in it. And it's 3 feet in diameter. It is moving at a very high velocity, say 10 feet a second, okay, maybe 3 feet a second. And it happens to be 15 miles long. How long do you think it's going to take to shut that pipeline down? Yes, my mother kept track of these chaps shutting down such a pipeline. And it took them a whole morning, 4 hours worth. And she was very upset that we had such lazy men working, shutting down that pipeline. Anyway, you know, big things take time. Big things take time. And that's a major difference in small scale and large scale. Right. You take a small baby, the baby's moving around all the time, especially when it's a toddler, right? It's into that and into this. Older people don't do that kind of activity, right? You take a small child, he's bouncing around everywhere. You can, parents just sitting there. So small scale, large scale, big difference. And you expect scale up to work? If the small scale tests fail, it doesn't rule out the successful operation on a large scale. Small scale tests, surface area is extremely important. Volume's not so much. Large scale tests, volume is important. Surface is not so important. It's an L over L squared for area, L cubed for volume. It's an L squared, L cubed effect. And if you want a design mistake, there it is. In sizing equipment, you have L squared, L cubed effects everywhere. If you don't pay attention to that sort of thing, you're going to pay a price. Small and large scale effects are different due to heat transfer. Heat transfer large scale versus heat transfer small scale. Small scale heat transfer is easy. That's why small people or small animals, well, let's just take people, will die in a blizzard, whereas larger people are likely to survive more easily in a blizzard. Anyway, there's all kinds of examples of where small scale rapid heat transfer versus large scale, which is the heat transfer, is very slow. Correct operating temperature, large scale, or lower than that indicated by pilot plants. Yeah, various things in here. Differences in size. Number one, small dryers limit particle size. Large dryers can produce coarse particles. There's a difference in particle size distribution. Difference number two, small dryers lose heat more readily than large dryers. This is what we were talking about. So you have differences in hygroscopic and thermoplastic materials. Difference size, difference three, a relationship between small and large scale dependent upon the product. Difficult to generalize relationships. Industrial experience is vital and proprietary. There you go. What's really funny about proprietary stuff is that, well, it could be extremely important, or it could be worthless, but it's proprietary. All spray dryers offer test facilities. I don't know if all of them do, but anyway, minimum pilot plant equipment, ability to conduct co-current tests, rotary or nozzle, ability to operate open, closed, or semi-closed, should have the ability to produce fines and coarses, should have the ability to handle aqueous and non-aqueous feeds, should have the ability to operate in a safe manner, represents a sizable investment. I like to always go on the cheap myself. My department head comes to me and he says, I got all this money I want to spend. And he says, why don't we buy new laboratory equipment for the unit ops lab? I look at him and say, sir, I'm an engineer. I don't need equipment. I can use what I have and do retrofits on it. He gets very upset that he can't spend his money or waste his money. Anyway, this is out of, I'm sure, Master's book. Master's obviously was a superior gentleman of great knowledge. There's no question about it. Anyway, test dryer, we have what are sizes? We want to look for size. 2.5 meters, different variations, 1.5 to 2 meter diameters, and down here 1 to 1.5 meters. 0.8 to 1 meters. There we go. So looks like we want 1 meter and above. Different particle sizes being produced, the atomizer, what type of heating, ancillary equipment. And the best place to get equipment quickly is used equipment market. Also, combine that, you buy the equipment and use the equipment people, and great bunch of people, I imagine. Take it to a local machine shop. You have control over everything. Get you a pilot plant real quick. The bigger the better for a pilot plant. No, actually you want to have versatility, and with things when you get very large become pretty much fixed. So to add versatility, you want smaller sizes. So you have a trade-off, right? There are some statements here about exhaust systems of all dryers permit installation of silicones, dry wet scrubbers. Bench scale studies before pilot plant studies. Well, maybe yes, maybe no. Select the formulations most suitable for scale-up tests. Select the most suitable atomizer. Select formulations for evaluation. Assessing the suitability of material to spray drying. Results obtaining represented powder samples, confirm operationability, optimizing conditions, determine ancillary equipment. Residence time. Now, this is personally from 1 to 10. I never did care for residence times. Essentially because I'm not quite sure whether they're all that useful. What? Residence times aren't useful? Well, case in point, I have a student comes into my course. 9 o'clock, he comes in, quickly falls asleep, sleeps through the entire course. Sleeps through the entire lecture. I get up, try to leave before he wakes up. I don't want to wake him up. It's horrible getting woken up. Anyway, I try to sneak out. Anyway, he's in there sleeping. So lots of materials will enter a tank and not participate in the operations in that tank. Obviously, spray dryers, that's not going to happen. Unless, of course, there's a side stream that trickles down the sidewall, which is from a plugged or a hole in the feed pipe, or misdirected nozzle, or one side of the wheel is got substantially more liquid coming off of it than the other side of the wheel, and I have a stream running down the wall. So all those are a violation of residence time. Then we got to residence time of the air. We could probably figure that out. Since the air is probably well distributed, you could take volume divided by air flow rate and get some sort of residence time for the air. Now then, the real serious question is, what's the residence time for the drops? How long does the water or the liquid run down the wall before it exits? Is it part of the product stream? Have you noticed it in the particle stream at the exit? What's the residence time of the drops? What's the residence time of the particles? Has there been wall buildup? Is there a dusting of the material on the wall? So the air residence time is probably pretty cool. I mean, you got that nailed down, but the particle residence time, now that's a real, how can I say it, conundrum. Anyway, so usually you have process volume divided by flow rate. Now then, if you break this down according to particle size, and you take individual particle sizes, their residence time is going to be huge. So flow rate of a certain particle size is going to be very low, and it's going to supposedly be in there for an awful long time. So you got to worry about hold-up volume of your particles, and that determines your residence time. So if you got the material at the tank bottom, and in the cone, and it's there for 20, 30 minutes before it comes out, and it's exposed to the conditions, then residence time for the product is another matter. Residence time for the product is the hold-up volume of the product in the chamber divided by the exit flow rate of the product. So air is easy. The residence time for the solids or the drops are a different matter. What's the residence time of a drop before it all evaporates? Hold-up volume of the product may not be known. Residence time is used determination of chamber volume. You got to have a flow rate. Chamber volume should have velocities, I suspect, below 60 meters a second, 60 feet a second, or below 30 feet a second, which is abrasion level velocities. So there's a certain chamber flow or velocities that I have. Determination of particle drying time from Lefebvre's book. It's often assumed that the minimum particle residence time is the residence time of the air. Well, that may be true, or it may not be true. Most products have a residence time much higher than the air residence time, so that drying can take place. There you go. Product exit flow is much smaller than air exit flow. Optimum residence time for a product is the time for the completion of desired moisture removal with the minimum increase in temperature of the dried product. The longer it's in there, the more likely it will heat up. It's sort of like if I take French fries, I've dried the French fries by boiling off the water in a fryer, right? So now the French fry has lost a lot of moisture and it's dried, and now it starts to brown. And it browns because it's at a higher temperature. It's no longer being protectively cooled by the evaporating water, and the temperature of the French fry increases and increases some more. And I get the burning reactions on the surface. Okay, so so your question is how long is the French fry in the fryer before it starts to turn brown or before it starts to turn charcoal level? Notice the residence time of a French fry in a fryer is much longer than the residence time of the evaporating moisture out of the French fry. So we have coarse sprays need longer residence time than fine sprays for the same moisture content. So coarse sprays means big drops, so depends upon the atomization ability of your atomizer, coarse versus fine. Lower drying temperatures or required residence time can be very long. The idea, tall towers. Residence times cover a range from 5 seconds to several minutes. Larger residence times usually mean bigger structures, bigger drying chambers. Short residence times, 5 to 20 seconds. Semi-dry state can withstand turbulent air handling, can withstand contact with hot air, can be dried in cyclone dryer. Long residence time, about 40 seconds, heat sensitive, need lower drying temperatures, cannot withstand high temperature air. Particles are free fall against the rising airflow, need tall countercurrent towers. Okay, countercurrent, if it's co-current, they quickly leave. Countercurrent, will slow it down a bit. Dried in co-current air, dryers in rotary air, 2 to 40 seconds. So we have a range of residence times here. Now, I'm going to clip through these. Summary is the steps for dryer layout and design. Well, the system, open, closed, semi-closed. This is getting away from everything we just talked about. This is a completely new subject. Dryer designs, well, up here you're going to have standard self-inertizing, Here we have countercurrent mixed, rotary, pressure 2 fluid, residence time short, long, medium. Any pretreatment. Inlet temperature selection. Obviously, got to spend some time to see what degrades your product. What degrades your liquid. Your feed may be quite protected by the liquid on it. Outlet temperature as low as possible. Heating input, direct or indirect. You do not want to have indirect drying unless you're required. All right, air dispenser, right? All kinds of air dispensers. Really, you want a swirling action, at least I would think you want a swirling action to keep things off the wall more. What side of things do you have in the way of particle collection? Whether you run wet cyclones, I would imagine wet cyclones are quite efficient in collecting particles. And you have chamber atomizer selections, minimum drying chambers at maximum evaporation capacities with rotary atomizers. Wow. Other components, heaters, fans, pumps. Other collectors, assessment of hazards can be quite enormous, right? Dust explosions and fire risks, minimum ignition temperatures in the cloud layer foam form. Minimum exposure concentration, minimum ignition energy, sparks right there. Maximizing explosion pressures, while oxygen concentrations where ignitions won't occur. The toxicity factor, chemical activity of the emissions. Where was it? I was at Jack Daniel's distillery, and for some reason these trees were coated with some of the products from the distillery. I don't know what it was. I don't know. Local fauna. Recognize safe procedures available on a crisis, safe emission limits, safe level of working environments. Safety and exception limits, extent of odor generation, deodorizing, and temperature. I would certainly visit the Chemical Safety Board videos on safety and just see if they have any dryer. They have dust explosions quite often, but then they have potential drying accidents that have happened. See if you have any information on that. Then any previous accidents recently. There are accidents blow up the plant, so then you don't have any place to go to work. You know what I mean? That's terrible when you ain't got a place to go to work. That's why you have to stay on with the wife, right? Anyway, particles, closed systems, and non-aqueous systems. Anyway, about your particles, what do you have? And I've gone through this with my crushing and grinding. And anyway, assortment of particles. I like this one. I have this particle distribution, and when I lose my static charge, they fall off. And now over here, size measurements. You actually believe your size measurements? I don't, right? But you should recognize two major areas of size measurements: the Stokes drag region and regions where you have large particles. So you have Stokes drag measurements, and then you have large particle measurements. I was listening to this chap talk about the device that the equipment that he had to sell about how to measure particle size distribution. And he was dealing with granular materials, and I asked him, what happens if you have a flake? A flake. And without skipping a beat, he said, multiply by 2.6. I was quite amused by his answer, anyway. Greater hiding power, greater strength, greater impact strength, smoother, irregular shaped, irregular sharp edges. You don't want sharp edges for an initiator, explosion initiator. And you want abrasive edges. So these are just some comments about solids. These are the actual particles, and these are simulations of the particles. The way it would help to realize that you can start worrying about particle shape. And what you're doing is you're adding all these harmonics together. Anyway, there's mathematics to that. Skip it. I sort of lifted this from crushing and grinding. Two extremes exist between the influence of the material and the dryer shape. Character being dried has little influence on shape. Spray dryer has little influence. The character of the material being dried has the most influence on its shape. Spray drying has little influence. Then on the other hand, you can have the spray drying methods most influential in shape, flow regime, and material properties have little influence. Right? So you have two extremes, the machine controls or the material controls. So reality lies somewhere in between. I thought that was kind of interesting. I lifted that from the crushing and grinding book. Right. And so we have non-solvent non-aqueous solid systems. Many materials are first produced in organic solvent. Okay, sometimes the solvent's replaced with water before drying. However, so air and water are not difficult, cheap, allows open cycle. However, in some applications, switching to water is not possible. So now you have to worry about solvent evaporation in a closed drying cycle, right? Cheap, low cost, many disadvantages. Okay, the idea is we do heating, we do the drying, and then we do the condensing, and we start all over again. Solids come out one side, the liquid comes out of the condenser unit as the other side. Feed comes in, basically hexane with whatever it's carrying. So this psychrometric chart is for hexane and nitrogen. So if you're going to have a solvent with another gas or with the gas, you got to come up with this psychrometric chart for that combination. So you grab a hold of a local thermodynamicist and you pay him a little money and out pops the psych chart for that combination. Or if you're fortunate to have a thermodynamicist in the company, you give them the psych, ask them to develop the psych chart for you. So we'll leave it at that. You got psych chart. I assume you can do that. Okay, major disadvantages, hazards in handling solvents. Design complexities of a closed system. Overall, drying solvents, another realm of drying water. It's another realm from drying water. You have exposure limits, lower explosion limits, and upper explosion limits. Anything above the upper explosion limit, right, should be considered unsafe because the upper explosion limit can easily be diluted down to where it reaches the explosion limit or gets to the location where it's an explosive mixture. So anything above UEL is unsafe. Anything between these two is obviously unsafe. Now, the lower explosion limit's kind of flaky, too, because, you know, I don't want to hurt your feelings, but gases separate, right? So the concentration in one layer of gas can be quite different than the concentration in another layer of gas. Case in point, there was a second floor where there were storage tanks for carbon tetrachloride. And so the top of the tank became saturated with carbon tet and overflowed along the side walls of the tank, went down to the first floor, and over the weekend formed a carbon tet layer, gas layer, down on the first floor. And then people came to work, started up the what do you call it, lift. It was gas powered high lift. And because the carbon tet layer was still below the ignition, there wasn't any accident. However, they left the machine on during lunchtime. The carbon tet got raised up to the level of the ignition due to it was gas powered, and the system exploded on them. So whenever you're dealing with gas, you got to watch out. It may separate on you. Have you ever seen fog in the morning? It's quite separated out for the rest. And with the upper explosion limit, the mixture can easily be diluted and reach the explosion limit. Gases can separate, heavier gases sink, lighter gases rise. Hotter gases rise, right? Colder gases sink. Gases are most often considered well mixed, but they're not. You gotta recognize nature's out to get you. I don't know if you realize this. Just from a pessimistic point of view, nature has a habit of reaching out and killing you. You gotta be cynical about whether Mother Nature likes you or not. So I am always suspicious. I'm suspicious. Never trust the obvious. Okay. Standard safety problem causes many, many explosions. Again, chemical safety board, you look under separated gas explosions and see what you come up with. The gas is 1/4, the LEL. It could be potentially separated in two volumes, one which is above the LEL, a lower explosion limit. Never trust the gas. Gas forms explosive mixtures with most solvents. The need is to avoid oxygen. Air can't be used as a drying medium of solvent systems. Drying gas or drying medium must not cause any problems with solvent or product. So typically you're looking for a non-reacting gas. You're looking for an inert gas that you can recycle. Nitrogen comes to mind. Carbon dioxide comes to mind. I'm not quite comfortable with methane either. These two I know don't burn. Methane, however, if there's a leak and methane comes out of the leak, you could have a little torch there at that leak. Might be an interesting way of identifying leaks. But again, I don't like that idea. The basic premise of safety is you really want to run scared. You want to run scared, okay? I don't know how brave you are, but I don't want to be dead and brave. Okay. Anyway, just a social comment there. Products or solvents may be hazardous, toxic, required closed system. Solvents may be valuable in recovery as an economic necessity. Most organic compounds are flammable. Recovery is by condensation. Examples are here. Sometimes it's cost effective to evaporate the solvent, even though it can be replaced by water. You know, you can just let this thing sit there and agitate it with an impeller, and you'll have natural evaporation occurring. So put that through a condenser and don't spray dry them. Solvents usually dictated by the process. Solvents could be suited to drying operations. Okay, the best way to avoid a difficult problem is, of course, go around it. Easy to use solvents, low latent heat, no hazards. It cannot be managed. Causes no drying problems. Well, agglomeration is a major drying problem. Solvents may be a mixture. There you go. Miscible or partially miscible. Now you've just raised the level of difficulty. Just as a comment here. Complex drying, low boiling comes off first. Higher boiling, right? Residual moisture. Information is sparse. Mixtures of solvents may be more trouble than they're worth. Condensation may be an issue. Yeah. Multi-component condensation is an issue. They can do a distillation column fairly easily, or they can design heat exchangers fairly easily. But a condenser with multi-phases in it, multi-miscible and immiscible liquids, varying heat capacities, varying boiling temperatures. It's quite an interesting device you have there. Okay, a mixture of solvents may be more problem than they're worth. Let's go on. Multi-component condensation is tricky. You have diffusion barriers form. Multi-component solvents are an alternative, but unlikely better than a single solvent. Efficient solvent drying, just like water, improved with higher inlet temperatures, lower outlet temperatures, improved with low duty, i.e. low inlet moisture. Again, I can imagine that with the solvent situation, decantation wouldn't hurt. Let it sit there and the moisture will flow out. Quality of drying gas determines equipment size. Approach to saturation determines product moisture. There we go. Solvent drying problems may not need spray drying. Initial drying rates faster than water because of latent heat. Solvents usually have lower latent heat than water, so they can evaporate just sitting there. Can cause problems, evaporates before the drop's formed. That would be like in cotton candy or putty string filaments, clustering discrete particles. If this happens, you don't need a spray dryer. Clusters may be held together through static cling. Hopefully, static charge. Hopefully there isn't any oxygen around. Clusters may have loose bulk density and are almost always unacceptable. There you go. Solvent drying, slow the drying rate and drop rate formation, possibly dilute the solution. Generally not a good idea. Lower inlet temperatures produce large drops. Okay, cooling gas may be introduced to contact the liquid and aid in the formation. Moisture content outlet gas can be 10 to 60 times greater than air or water. I mean, evaporation, that's a lot, basically. Lower the evaporation rate by lowering the driving force for evaporation. Need to get the saturated gas out of the drying chamber. Often the solids have an affinity for the solvent. This causes the solid to have a higher moisture content. Lower moisture contents could be reached with higher outlet temperatures for the gas or for the solid and gas. Longer exposure times and secondary follow-up dryer. Even traces of solvent may be unacceptable. I mean, can you imagine getting instant coffee with tastes of hexane in it? I don't even know if hexane is permitted anymore. Must be something else they're using. This is the opposite there. Water drying, retained water is generally harmless or serves a useful purpose. Closed systems requirements, recovery of solvent because of its value, safety, environmental reasons, prevent explosive mixture of solvent with air, recycle drying gas because of its value. Well, it's all the solvent, recovery of all the solvent. prevents vapor escape, sparks, or other initial surfaces. Dry to low moisture content, avoid harmful effects of solvents in the product. Provide necessary precautions for toxicity and hazards. Heater should be indirect, right? Indirect dryer. We went over indirect drying. Amount of bleed should be much smaller than the air-water systems. The amount of bleed, if you have a bleed, is that it passes through a flame. Scrubber serves as a backup collector and condenser. Okay. Fed solvents to cool gas sufficiently to condense the vapor. Feed is the same as solvent as the feed. Tubular condenser should be used, but would suffer from a very low heat transfer rate due to low pressure inert gases. Design, okay. Take a look at some design. You have to consider the properties of each solvent. Design, separate the solvent from the solids, separate the solvent from the gas, recycle the gas. Need to prevent O2 buildup, leaks in or creates explosive mixtures, or in or out, create explosive mixtures. Outward is self-indicating, less dangerous. You don't want buildup of oxygen, it's a big one. Outward leaks are self-indicating, less dangerous, occurs with systems that operate with positive pressure. Oxygen levels should be analyzed on a continuous basis with special care during startup. Startup, right? The whole bloody thing is filled with air, right? Hazards of solids, mandate extreme caution in handling and equipment. Design gov regs exist for some solvents. Environmental controls exist for some solvents. Special problem not recognized. I don't know if it's not recognized or not, but static charge buildup. Just pumping a solvent through a pipe can cause a spark. Okay. Now then, the question is, well, what do you use with that spark? If you have no oxygen around, you're okay. One case in point, benzene through a plastic pipe, lit up like a fluorescent light tube, right? Light bulb. And if it had oxygen, God bless the area, right? Because it would be altered. Could ignite an explosion if released. Need to ground everything. Ground cables from flanges around flasks, ground everything. Use non-sparking moving parts and tools. Dun, dun, dun. Explosion proof, so they claim. I like explosion proof, right? It's explosion proof until it isn't. Non-sparking motors, minimize leads, good flanges, seals, double mechanical seals. Air gas cooling, purging used. Bag houses uses inert gas. You might collect up that inert gas. Produces gas to be bled out. Any introduced gas has to be bled out. Cost? Drying volumes much lower than water systems. Latent heat of vaporization is much smaller. Much higher ratio of solvent to gas. Much higher carrying capacity of the gas to take away the solvents. Almost always lower energy costs in small vessels. Again, you have a single solvent and solids, you just put it in a pot, make sure everything's stirred up, and draw a vacuum or heat it a little bit and have a condenser at the top, and away you go. You avoid spray drying altogether. You don't want to complicate things. You want to keep it simple. KISS principle, right? Costs for total system operating costs may not be lower. Additional add-ons, closing the loop, adding a condenser, providing explosion venting, indirect heaters, upper limit, maximum drying temperatures, 3 to 450 C or 425. Additional items may need to rework the solvent by distillation, right? Special building features, explosion venting, explosion-proof equipment, higher insurance costs. You want to put this in what, explosion-proof facilities. In other words, if there's going to be an explosion, you want to direct that explosion to a certain direction. Bunkers is what you call them, right? Anyway, higher insurance costs. Interesting twist. Sometimes it's possible to use a solvent as a drying gas. This eliminates inert gas requirements. Solvent has to be superheated, much smaller equipment. Condensing simple without inert gas. One requirement, dry outlet has to be well above the solvent boiling point, right? Which means you're going to be at high temperatures. Prevents condensation in the dryer. May be difficult to reach. Desired moisture content may require a second dryer. Nothing wrong with staging. Clean up. Example, clean up. Use of solvents in closed system. Right, you need the right equipment. Solvents represent a toxicity problem. Solvents also give off toxic monomers. Product receiver needs monitoring. A product with incomplete drying gives off vapor and forms an explosive mixture. And the collector, often difficult to seal collector completely or adequately. Okay, I just thought I'd throw out some of these. Obviously, 2008 is a long time ago. And they claim this is recent develops in spray drying. So we have these chaps, all very capable people, I'm sure. What's interesting is look at this stuff they're spray drying and creating. Jeez, oh man. Look at that thing. Boy, that's got to be unique. That's fairly interesting as well. Then we have these things. Jeez, oh man. You see the spheres have puffed up and then shrunken down. There must be an exit hole somewhere. Similarly here, these things started out as a very big sphere. And as they cooled down, you had diffusion, whatever, coming out. Really cool stuff, huh? Spray drying CFD, there's a book on it, I think. Here's in a book. Yeah, that's your assignment. I want you to buy this book and read it. Right? It's probably 2 or 3 inches thick. 10 pages a night. Bring you up to the recent stuff in spray drying. And of course, I love YouTube. It's one of the reasons why my videos are on YouTube. I think it's very fascinating, all the information that's on the YouTube. Sort of like going to school. On YouTube, you can see ligaments breaking. You can see breakup of liquid jets, impinging jet diameters, 2-fluid nozzle stuff, dancing water sprinklers. They have one where they have 2 jets meeting, creating droplets in space, and then they cross-section the computer simulation. Okay, and fantastic video. OSOG number, they also have a video showing OSOG's OHSORGE, I think. Maybe the spelling may be weak. OSOG also has videos. They have OSOG at 1, 10, 100. Pretty cool. Anyway, I leave videos. YouTube again, fantastic. And I guess that closes it out. And I leave you with happy drying to you, spray drying to you. And again, the major books that I use, Cook and Dumont. I was fortunate enough to work with them. They're a great bunch of guys. Masters, I was too young to know. And Wallace did a fantastic job with his chemical process equipment. The first book came out, it's a really great book. And of course, I'm sure these guys did something to improve it, but anyway, again, the videos, I love these surface tension videos. And you can watch those SOG number videos, it's great. Well, that concludes my spray drying lectures. I hope you enjoy them. I hope it makes you gives you some information on. I hope I helped you out with your spray drying. Anyway, I'm going to turn it off and stop the recording now.